Hello guys, welcome to BYJU'S Exam Prep, the most comprehensive preparation app for all the competitive exams. So today I am going to teach you instruction pipelining. So I hope I am audible and visible to all of you. Am I audible? So please confirm me once. Is my audio, video, everything is clear? Am I audible? Okay. Yes. I once again welcome you all to the BYJU'S Exam Prep and warm welcome to my class that is on instruction pipelining. So already we have started this series in the last class, the basics of computer organization and architecture I discussed. And let us continue that, and I'm starting some typical topics. So that is instruction pipelining I will teach in 3 parts, and also catch organization I will teach in 3 parts. Okay. So please join quickly and mark your presence. Yes, Prabhakar, good evening. Thank you for your response. Am I audible? So please confirm me once. Is my audio, video, everything is fine? Please use the chat box for communicating with me. Yes? Okay. So before I begin the session, so let me introduce myself. Myself, Murali Krishna Bokasamudram. I am having 21 plus years of teaching experience, both in the GATE and also I worked in different engineering colleges. And these are some of my credentials. I am a topper in NPTEL course and also certified as International Engineering Educator through ISE certification program, and I have taught more than 50,000 students across the country for GATE and other competitive exams. So in the areas of computer science like theory of computation, operating system, computer organization, computer networks, digital logic, and information and communication technology. Yes, Abhijit Singh, good evening. Yes, please, before I begin the session, please do share this class information with your friends and also subscribe the channel if you have not yet done it. We are providing free content for the GATE aspirants, and we are having different series like GATE 2024 fundamental series is there, and for NIELIT also parallelly series is going on, and basic mathematics and also some general sessions we are providing, motivational sessions and also post GATE guidance. All these things we are providing. Please try to make use of this, and we are coming up with a lot of other ideas for the coming month, like tips and tricks for the GATE and all, and so preparation tips and all. So please do subscribe the channel for getting more notifications. Please plus the bell button. Okay. Yes. Good evening, Abhijit. I hope I am audible and visible to every one of you. So please share this class information with your friends. Yes, in all the your social media groups you can share so that your friends can join. Fine. And these are the toppers of 2023 GATE, and let us congratulate all these toppers. We got 62 students under All India rank 50 and 13 students under All India rank 10, 107 students under All India rank 100. There are 3 people who are on top ranks, that is Dhruv is having All India rank 5th in computer science, and SH Gautam is the first rank All India rank in P&I, and Sar Verma has got All India rank 4th in the instrumentation, 5th in the electrical. So big congratulations to all these toppers, and I wish you all the best for all the aspirants of 2024 and NIELIT 2023 and also the ISRO aspirants. Okay, I hope I am audible and visible to all of you. So shall I start the session? And this instruction pipelining is one of the typical topic in computer organization. So that's what I am taking up. In 3 parts, definitely you will get confidence if you attend all the 3 parts continuously. And every day evening 9 p.m. I am taking the class. And don't miss any of the class. Okay. So shall I start the session? So please do respond in the chat box, and also after the finishing of session, I will continue replying your doubts in the comment box also. So please try to make use of this facility, right? Okay, so now I'll be starting. Okay. Yes. Good evening, everyone. Okay. Just share this information with your friends so that your friends also can join. And don't forget to do subscription if you are not yet done it. Fine. So before I begin this instruction pipelining, just let me explain. So different basic concepts related to instruction pipeline. So basically, actually clock cycles we use for the execution of instructions for different stages. Okay. So any instruction should be executed in a multiple stages, right? So like fetching of instruction, decoding of instruction, okay, and then execution of instruction, and then writing the operand in a some register or in memory like this. So there are different stages in the instruction cycle. Each stage is requiring different cycles, right? Okay. So before I begin, you should understand what is a clock cycle. So this terminology you have to understand. Okay. So clock cycle is nothing but actually in a computer system, there is a master clock pulse generator. It will generate the train of clock pulses like this, what I have shown like this. So there is a rising edge and again falling edge, again rising edge and again falling edge like this. Train of clock pulses are being generated by the master clock pulse generator, and these are used for synchronizing the entire operation. Okay, so this is nothing but when the signal is moving from 0 to 1. Okay, and the pulse is moving from 1 to 0. Okay, so 1 to 0 and 0 to like this, there will be up and downs. Okay, and if you take any of the, for example, this one, and this is the up and this is the down, that means positive and negative. So moving the value from 0 to 1 is a positive, and moving the value from 1 to 0 is a negative triggering. Okay, so here if you wanted to know what is the cycle, so what is the cycle time? Cycle time is depending upon the frequency of the processor. When you buy a computer, okay, configuration you will see, right? In the configuration you will find out processor frequency. So like this, if it is a slow processor, you may have like 200 megahertz of frequency, and some processor may be having 250 megahertz of processor frequency, and some processors may be having 1 gigahertz of clock frequency like this. So clock frequency is important in executing the instructions faster. Okay, when the frequency is higher, the cycle time is lower. So cycle time is inversely proportional to the frequency. Cycle time is inversely proportional to the frequency. So a processor with high frequency, it takes less time for a cycle, so that it takes less time for finishing the execution, because every program takes some CPU cycles to finish the execution, right? Okay, in this we may take positive edge or also negative edge. If you study the digital logic, you might have understood. For example, if you take this timing, this time gap is from first positive transition to the next positive transition. This is the first negative transition to next negative transition. This is negative edge triggering, and this is positive edge triggering. When a clock pulse is moving from one positive transition to another positive transition, how much time it is taking? So that depends on the frequency. If the frequency is higher in a less time, so faster they will generate the cycles, so that the execution time also faster. Okay, so if I teach you what is the cycle time exactly in nanoseconds or microseconds, you can take one example. For instance, if I am taking like this, listen carefully. Let us suppose I am taking a 1 gigahertz processor, and what is the cycle time for a 1 gigahertz processor? I'll just show you. So one cycle time, let us suppose processor speed is one frequency, not speed, frequency is 1 gigahertz. So one cycle is equal to, in this processor, one cycle is equal to 1 by 1 giga is nothing but 10 power 9 hertz. 1 by 10 power 9 seconds. When it is given in hertz, the cycle time is in seconds. Okay, 1 by 10 power 9 seconds is nothing but 10 power minus 9 seconds. 10 power minus 9 seconds is equal to 1 nanosecond. 1 nanosecond. If you take other than, for example, processor is having only 250 megahertz, for example. So in this processor, one cycle is equal to, as per the cycle time of the formula. So 1 by 1 mega is nothing but it is a 10 power 6. 1 by 250 into 10 power 6 seconds. If you convert into nanoseconds, you have to multiply with 10 power 9, so that 7 zeros will be cancelled, and then it will be 100 by 250. It is 1000 by 250. You will get 4. So one cycle time is 4 nanoseconds in the case of a processor with 250 megahertz frequency, and 1 gigahertz frequency 1 nanosecond. So how faster it is? So 1 gigahertz frequency is 4 times faster than the 250 megahertz. Okay, so this is what the cycle time is. and because computer system requires some cycles for execution of these instructions. Are you following? And if you have a doubt, please ask me. And usually, yes. Nobody is asking doubts. Please try to ask your doubts as and when you get doubts, please. Okay. You're able to follow? Yeah, that's great. Fine. Okay. Now, different stages are possible in the instruction cycle. Okay. So usually the basic stages like fetching of instruction. What do you mean by fetching of instruction? Getting the binary code from the memory and keeping it in instruction register. And after fetching, we need to decode the instruction to understand what type of instruction it is. Then after understanding what type of instruction it is, we can execute. Performing the operation is nothing but execution. And then writing the operand. After performing the operation, we have to store the result somewhere. So every instruction should go through all the stages. Not only for some implementations will define whether it is non-pipelining or pipelining. The stages are required. Every instruction must go through all the stages. How they are going, whether sequentially or in a pipeline, that depends upon the kind of methodology we adopt. Okay. So whether it is non-pipelining execution or it is pipelining execution. So during the write operand stage, we are supposed to store the result. Whatever the result we got, we are supposed to store the result either in memory or in the register. During the execution phase, we have to perform the actual operation, whether arithmetic operation, logical operation, loading of data, whatever it is. During the decoding of instruction, we will try to identify what type of instruction it is, classify by using the decoder. And during the fetching of instruction, binary instruction code we get from memory initially, and we have to keep that in the instruction register before it is decoded. So this is the sequence. So different implementation may have different types. We may have a 4-stage instruction pipelining or a 4-stage non-instruction non-pipelining, 5-stage pipelining, 6-stage pipelining like this. So typically we will have the stages like this in a typical system, like fetching of instruction, decoding of instruction, fetching of operand also required. Fetching of operand is a separate stage where we get the operand. Before performing operation, we need operands. So that is fetching of operand. And whatever the operands available, we perform operation on those operands. That is called execution. WO means writing operand. And the calculation of operand address also can be taken as a separate stage. So each stage requires a separate hardware setup for performing those tasks. Okay. And for example, if you take multiple instructions, same stage cannot be done by multiple instructions because same hardware is required. Okay. So in a non-pipelining, instructions are executed in a sequential fashion, and in a pipelining, instructions are executed in a overlapped fashion. Hope you are following. So why I have shown this slide? Because to understand the stages in instruction pipelining. Okay, so some implementation may have 4 stages, some implementation may have 5 stages, some may have 6 stages like that. Usually when the number of stages are increased, pipeline will do better because more overlapping is possible. I will show you the outcome of increasing the number of stages. Hope you are following. Okay, if you don't follow, please ask me. I will just clarify your doubt very clearly. And yes, this is very important session. I think you can inform your friends and do subscribe the channel and press the bell button for getting the notifications, right? Okay. I hope you are aligned with my teaching, and if you get any doubt, don't hesitate to ask your doubts. Yes, fine. And please do like the session if you are really liking it. Now coming to what is a non-pipelined execution. Non-pipelined execution is very simple. There is no need of overlapping. It's like this. There is no overlapping in the execution of instruction. For example, if there are 4 stages, FI, DI, FO, EX, let us assume. So what activity is being performed in each stage, you will understand in detailed discussion. Okay, FI, DI, FO, EX, it is a short notations of fetching instruction, decoding instruction, fetching of operand, and execution of instruction. Okay, and we are assuming that one cycle is taken for one stage, let us suppose, just for understanding the purpose, and some stages may take multiple cycles also. Okay, it is like this. In the non-pipelining, after finishing the execution of all the stages, for example, at a 4th stage, we could finish the first instruction I1. Then after this point only we can fetch the next instruction. So fifth cycle and at 8th cycle second instruction got finished, and at 12th cycle third instruction got finished. Like that it will go. That means after finishing all the stages of one instruction, we took the next instruction. So there is no overlapping. Every cycle is doing only one stage, not multiple stages parallel. There is no parallel execution. That is what is non-pipeline execution. It is also called as the sequential execution. It is also called as the sequential execution of instructions. Hope you are understanding. Okay. So nowadays, how the computers are making execution very faster because of all these pipelining implementations and parallel computing only. If you could understand what makes the difference among non-pipelining and pipelining, you can easily make a difference, and you can invent a new computer where it can do more faster than the existing computer, right? Okay, now, are you having any doubt? And what is this clock's cycle number? Cycle number 1, 2, 3, 4. So just for understanding easy representation purpose, I have taken an example of every stage is taking one cycle. Okay, one cycle, but different stages may take different cycles also, different timings also. Okay, that is quite possible. Okay, so that is the criteria. Now let's move on to the next slide. So how many instructions I am executing here? Any number of instructions, but every instruction take 4 cycles. If you execute 1 lakh instructions, 1 lakh into 4 lakh cycles will be taken like this. For example, if I execute 1 lakh instruction, every instruction take 4 cycles, no overlapping, 4 lakh cycles will be considered here. Now, non-pipeline execution, if you do with the 6 stages like fetching of instruction, decoding of instruction, calculation of operand address. Calculation of operand address means what? Can anybody tell me? It is finding the effective address of operand where it is available, whether it is in memory or in register, effective address. After finding the effective address, we have to fetch the operand, means getting the data from memory or register wherever it is available. And then execute. Execute is a performing operation, and then write operand for storing the result. So these are the things. So instruction I1, first all the 6 stages, so it is done. Then we have started the instruction 2, and at 12th cycle second stage is done, and similarly at 18th cycle third instruction will be getting finished. Like that every instruction is taking 6 cycles. If you assume that one stage is taking 1 cycle. So like that, if I execute 1 lakh instructions, it will take 6 lakhs obviously, because sequentially they are executing. So when the number of stages are more time it will take in the non-pipelining system. But we can take advantage of pipelining for a number of stages more. Okay, so that is what I am going to explain right now. Now the pipelined execution. In a pipelined execution, instructions are executed in a overlapped fashion. So for example, let us consider 4-stage instruction pipelining. Hope you are following. 4-stage instruction pipelining. What are the stages? Fetching of instruction. What we do in this stage? We get the instruction binary code from memory and we keep it in the instruction register. That is one special purpose register. Then by using the decoder, we decode it to understand what type of instruction it is, like opcode, mode value, address part, everything. And after knowing the type of operand, type of instruction, to perform the operation, operand is required to be obtained separately. So sometimes operand may be available within the instruction. That depends on the mode of address. Sometimes it is in memory, sometimes it is in register. That depends on the instruction format. So fetching of operand is nothing but what? Getting the data to perform the operation. And execution is nothing but what? It is to perform the actual operation in the arithmetic logic unit based on the type of opcode given. Hope you understood, right? Okay, so shall I go ahead, and do you have any doubt on this? Now if you see this, instruction I1 executed at 4th cycle, it got finished. But have we started the instruction I2 in 5th cycle? No. We have started I2 in 2nd cycle only, because while I1 is in fetch, I2 cannot be fetched, because 2 instructions cannot do the same stage at the same cycle. But we can keep the second instruction in a buffer. So pipelining buffers are required actually. Additional overhead is required to keep the buffers in between the stages. But whereas in a non-pipelining, pipelining buffers are not required. Okay. So while the instruction I1 is in decoding second stage, instruction I2 can come to the first stage. While the instruction I2 is in the second stage, instruction I3 can come to the first stage, like this. Now, if you observe at a fourth cycle, from the fourth cycle onwards, all the stages are overlapped. Instruction 1 is doing execution, instruction 2 is doing fetch operand, instruction 3 is doing decoding, instruction 4 is doing fetch operand. All these can be overlapped because there are different hardwares required for doing the different stages. Okay, from fourth stage onwards, fourth cycle number onwards, okay, every cycle is overlapping with all the four. That means you are able to do 4 stages parallelly, means one instruction you are able to execute in only one cycle, right? If you can wait up to third cycle, after third cycle, in a fourth cycle, first instruction finished. In a fifth cycle, second instruction got finished. In a sixth cycle, third instruction got finished. That means one cycle is taken for one instruction, except the first few. But when you consider the relatively large number of instructions like 1 lakh, 10 lakhs, millions of instructions, then the first 3 cycles is not a matter. From fourth cycle, that depends on the stages. If you have a 6 stages, from sixth cycle onwards, so you keep on overlapping all the stages as much as possible. By considering the stall cycles and hazards and all, that is additional overhead. But of course, some of the implementational issues will be there. So, but in normal conditions, ideal conditions, the main idea of doing this instruction pipelining is to execute the instructions. Every instruction should finish in only one cycle. That is the idea. So that means maximum overlapping to bring. Okay, now got my point? So if you execute these instructions, for example, if you execute 1 lakh instructions, for example, if you execute 1 lakh instruction, how much time it will take? For the first instruction, it is taking 4 cycles. Thereafter, one cycle for every instruction. So 4 cycles plus remaining how many instructions? 99,999 into 1 cycle only. So that is nothing but 1 lakh 3 cycles. Okay. 1 lakh 3 cycles. 3 cycles is negligible in 1 lakh. So we can say that non-pipelining takes 4 lakh cycles. Pipelining takes 1 lakh. That means for a 4-stage pipelining, okay, and if you implement non-pipelining and pipelining, if you compare, so pipelining is 4 folds better than the non-pipelining. That means 4 is a speed up. These are ideal conditions, but I am not considering the implementational aspects like buffer delays and hazards and all. I have not considered. Only this is a basic thing. I hope you understood. So not only this class, I planned 3 classes. Tomorrow, day after tomorrow also classes will be there. Part 2 and part 3. And don't miss them. And please attend regularly. Okay. And please do share with your friends. Okay. Shall I go for the next slide? Did you understand what makes the difference between non-pipelining and pipelining? Okay. Now, what is the pipeline execution by taking 6 stages? So here for 4 stages, we got 4 times better. For a 6 stages, pipelining is 6 times better, because when you execute 1 lakh instructions, only it will take 1 lakh 5 cycles, but whereas in the non-pipelining, it will take 6 lakh cycles. So it is 6 times better. So instruction I1 got finished in 6th cycle. Only for the first instruction, it takes 6 cycles. Remaining 99,999 cycles, only 1 cycle for each instruction. Like second, done in 7th, it is done, right operand. 8th, second instruction, third instruction, 9th, 4th instruction, like that they are finished. So from the 5th cycle onwards, all the 6 stages are overlapped. 1, 2, 3, 4, 5, 6. Okay, like this. Fetching of instruction, execution, right operand, fetching, decoding, from here onwards actually. Somewhere from the 6th onwards it will come, because fetching instruction will come here. From the 6th instruction onwards, all 6 cycles will be overlapped. Fetch instruction, decoding of instruction, okay, calculation of operand address, fetch operand, execution of instruction, right operand, like this. Okay, now, so at 6th cycle, first instruction got finished. Thereafter, one cycle is taken for each instruction. So we got 1 lakh 5 cycles for 1 lakh instructions. Okay, got it? Done. Shall I go for the next? Yes, everybody is fine with this. That means, what did you understand? When the number of stages are increased, pipelining can do better than non-pipelining. with less number of stages. C rather than less number of stages. If a pipeline you take n stage pipelining, okay, it can do n times better than the corresponding non-pipeline. An n stage pipeline can do n times better than the corresponding non-pipeline. Okay, shall I go for the next? So please do respond. That gives a lot of interactive flavor, so that I also can continue with more energy. If you can respond in the chat, okay. And what is the speed up ratio? I told under ideal conditions, non-pipelining time divided by pipelining time is the speed up ratio. So time taken for non-pipelining, if you execute 1000 instructions, for example, time taken for 1000 instructions by non-pipelining divided by time taken for 1000 instructions in a pipelining. Or else, if nothing is given, number of instructions are not given. So ideal conditions, time taken for one instruction in a non-pipelining divided by time taken for one instruction in a pipelining. Usually all the stages are getting overlapped in ideal conditions for a pipelining, so that one cycle for one instruction if there were no hazards. Okay, and if you consider buffer delays negligible. For instance, one example I'll tell you. There are 4 stages and clock cycle time is 10 nanoseconds, buffer delay is 2 nanoseconds, and I wanted to find out the speed up. So how to find out the speed up? Non-pipelining time divided by pipelining. So in non-pipelining also all the 4 stages will be there. One stage is one cycle by default if nothing is given. So NP is nothing but non-pipelining. So it will take 10 nanoseconds for the first stage fetching, 10 for decoding, 10 for execution, and 10 for write operand. So total 40 nanoseconds. Under pipelining, P means pipelining. I'm just short form I'm using. So pipelining, actually all stages get overlapped, only one cycle is sufficient, and buffer delay we have to include. So it's a 10 plus 2, so 12 nanoseconds. Okay, now usually for a 4 stage and ideal condition, the actual speed up should be 4 for 100% efficiency, 40 by 10, but 2 buffer delay is there, that is included. Now the speed up is equal to 40 divided by 12. How much it is? 12 3s 36. Again 40. So 3.33 is a speed up. So speed up is reduced because of the buffer delay. Okay. So that is how we find out the speed up. And similarly, this is already I have explained. So buffer delay 2 nanoseconds, speed up is 3.33. And examples of speed up ratio, let's continue with other example. A pipeline P is found to be 5 stages. The clock cycle duration is 10 nanoseconds. If non-pipelining clock also has the same duration, then what is the speed up pipeline if its efficiency is 80%? So usually for 100% efficiency, what is the speed up? For 100% efficiency, speed up is equal to 5. How speed up is equal to 5? Can anybody tell me? Because there are 5 stages. Every stage is taking 10 nanoseconds. So one instruction execution time is 50 nanoseconds. Are you following? Yes or no? One instruction execution time is 50 nanoseconds in NP, non-pipelining system. In a pipelining system, and only 10 nanosecond, one cycle all are overlapped, so it is a 10 nanoseconds. So 50 divided by 10 is 5 actually, and buffer delay also negligible consideration for 100% efficiency. But actually he is saying that efficiency is only 80%, so it is just simply 80% of 5. So actual speed up is 80% of 5, so 0.8 into 5, it is nothing but 4. So 4 is the speed up for 80% efficiency. Okay, now coming to throughput. Throughput is very simple. How many instructions we are executing per a unit of time is nothing but throughput, whether it is non-pipelining or pipelining. So number of instructions executed per unit. So that unit may be usually seconds. For 1 second, how many instructions you are executing is the criteria. So that is the most important thing for you to understand this throughput. Let us suppose non-pipelining execution I am taking. Let us suppose there is an instruction. I am taking an instruction. Different stages are taking different timings. For example, stage 1 is taking 10 nanosecond of time. Stage 2 is taking 12 nanosecond of time. and stage 3 is taking 5 nanoseconds of time, and stage 4 is taking 8 nanoseconds, and stage 5 is taking 15 nanoseconds. So in a non-pipeline execution, after all the stages are finished of one instruction, next stage will start here. Again, next stage will start here. No overlapping. That means one instruction execution will take 50 nanoseconds or millisecond, whatever is given for non-pipelining. Okay. So for a pipelining, we do like this: S1, S2, S3, S4, S5. Again, S1 comes here. So there is overlapping. When all overlap, then when different stages are taking different timings, we have to provide a maximum value. That means maximum value of 10, 12, 5, 8, and 15. 15 is the maximum value. So every cycle time we have to provide 15. Okay, now. So if you provide 15, all the stages can be overlapped. All the stages can get overlapped. Okay, now. So now in 15 nanoseconds, actually it's not a millisecond, actually it's a nanosecond. I will show you the estimation of throughput here. If you wanted to find out throughput also, it's like that only. Pipelining is maximum of this 15, and non-pipelining it is taking 50 nanoseconds, sum of all these. Same example I am taking. So 10 plus 12 plus 5 plus 8 plus 5, 15 is 50. Non-pipelining time 50, pipelining is 15. So 50 divided by 15, 3.33 is the speed up. Okay, but throughput you have to find out. How to find out throughput? If we take a throughput of non-pipelining, so one instruction is sum of all these: stage 1, stage 2, stage 3, stage 4, stage 5. We are taking 50 nanoseconds. So within 50 nanosecond, only one instruction you can execute because of no overlapping. So 1 nanosecond is 1 by 50 instruction. 1 nanosecond is nothing but 10 power minus 9 second is 1 by 50 instruction, and 1 second is 10 power 9 divided by 50 is nothing but 20 mega instructions per second. How it is 20 mega instruction? Because 1000 into 10 power 6 divided by 50, 10 power 6 we can write it as 1 mega. So 1000 by 50 is nothing but 21 m is nothing but 10 power 6, 1 mega. So 20 mega instructions per second we can execute. That is a throughput in a non-pipeline. Non-pipeline throughput is less when compared to pipeline throughput. Now you can see pipeline throughput. So pipeline, different stages are taking different timings, so that maximum cycle time is provided, that is 15 nanoseconds. So throughput of pipelining, it is throughput of pipelining. So in 15 nanosecond we can execute one instruction. 1 nanosecond 1 by 15. 1 second is 10 power 5 by 15. So 1 mi is 10 power 6, right? So 1000 divided by 15 is nothing but 66.66 mega instructions per second. So where is 20 and where is 66? So it is far better, no? Because of the pipeline execution. So that's how we find out the throughput. Now, can anybody tell me what is the answer for this question? A 4-stage pipeline has stages like instruction fetch, instruction decode, execute, and write operand stages. The stage delays for different stages are different. So 5, 12, 8, and 10 nanoseconds respectively. The pipeline buffer delay is 2 nanoseconds, which is not required for a non-pipelining. So what is the speed up of the pipeline when compared to the corresponding non-pipeline execution? So please tell me what is the answer for it. I am just expecting this answer from every one of you after explaining these concepts. Are you following? Am I audible and visible to every one of you? Are you doing it? Okay. Please solve on this. And I will also give you one homework problem. You can discuss that in the comment box also. Yes, fine. Now coming to fine. 4-stage pipeline. What is a non-pipelining time? So there is no overlapping. Sum of all the stages we can consider. So it is a 5 plus 12 plus 8 plus 10. 20 plus 10, 30 plus 5, 35 nanoseconds. Non-pipelining time is equal to 35 nanoseconds. And pipeline time, we have to take maximum of this. So maximum of 5, 12, 8, 10, it is nothing but 12. 12 nanosecond is the maximum. Okay, so speed up is equal to non-pipelining time 35 divided by pipelining time 12 plus buffer delay of 2 nanoseconds should be added. So 35 divided by 14. Okay, na? So 14 2s 28, 14 5s 70. So exactly it is 2.5. 35 divided by 14 is nothing but 2.5. Option D is the right option. Okay. So that's all. Actually, I am providing this, and please try to go through this video once again if you get any doubt, and you can do the comment in the comment box. Thank you so much. Please do share this information with your friends, and do subscribe the channel. Thanks a lot. See you all again. Good night. Tomorrow at the same time, I'll be taking part 2. Please do attend. Thanks a lot. See you all.